Hello everyone. In this video, I'm going to introduce some of the concepts of reinforcement learning by taking game of chess as a running example. Let's get started. Hope you all are familiar with the basic rules of chess and basic how chess game is played. Let us assume you are playing chess game and you are white and you are in the middle of the game, and this is the current board position. At this board position, white to move, and what is the best move for white? What is the best move for white? If you see the list of possible moves from this board position, you can move the a3 pawn one step forward, or a b4 pawn one step forward, or an f4 pawn one step forward, or you can move the king in either of these directions one step. Okay, in total we have like 8 possible moves at this current board position, and out of these 8 possible moves, like what is the best move for white? Now, how do you find the best move? So there are a couple of options. Option 1 is like rule based. So in the rule based one, like you study the theory of chess and you study about some of the tactics or strategies, things like connected pawns, isolated pawns, king safety, etc., and come up with a set of rules and put it into a computer program and evaluate the current board position and then find the best move. So that is a rule based method. And option 2 is using data, simulations, and through experimentation. So it goes like this. Start from a particular board position. That position is called state, and play millions of games till end. So that is called episode, one complete episode. So you start from a particular board position and play millions of games till end, and you calculate the win percentage out of those millions of games. And what you are trying to find here is you are trying to find the value of a particular state or a particular board position by calculating the win percentage. And this method is called Monte Carlo approximation. It is like you want to find out the value of something, and it is difficult to find the true value of something, or you don't know what is the true value of it. And one way to find is like you run simulations, or like you run a series of experiments and you collect some data, and from that data you approximate the value of a particular thing or a particular state here. So this method is called Monte Carlo approximation. So once you have for a particular state what is the win percentage or what is the value of that state, you find the best move based on the win percentage or the value of that state. And the thing is, as we play more and more games, we get better approximation for the state value, that is like for a board position, what is the win percentage. Let's go through this example. Suppose you are in this position, you are currently at this board position, and these are all the possible moves as explained in previous slides. Let us take this rightmost position. Let us assume like you move the pawn a3 pawn one step forward, and you continue the game from there, and you played 100 games from this position, starting from this position. So out of these 100 games, like you won 90 games. So the win percentage for this position is 90%. Similarly, for this board position, like let us assume like you move the b4 pawn one step forward, and you continue playing 100 games, and out of these 100 games you won 60 games, and the win percentage for this position is 60. Similarly, for this position, the win percent, let us assume it's 10%, and for all these king moves, like the total win position is like, let's say, 40%. And like at the bottom you see the normalized win percentage. It is like you divide by the normalizing factor 20, so that like all the percentage, all the ratios will add up to, will sum up to 1. So 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 this is like just take a particular position, go with that particular position, play hundreds of games, and keep a count of like how many games you win, and keep track of what is the win percentage for each of these board positions. Once we have such a kind of data, now how do you choose the best move for this position? Like these are all the win percentage, and what is the best move to for white to move? Obviously we will select the position which is giving better win percentage. Like in this case the rightmost position is the best move for the current board position here, right? Cool. Now collect the training data, collect some training data, like for each state, for each board position, what is the win percentage, for each state what is the in value of that. So you collect some training examples like this: state 1, this is the value 1, state 2 value 2, state 3 value 3, state 4 value 4. You collect some training data like this and train a neural network to predict the value for a given state. You train a neural network to predict win percentage for a given board position. And once you have trained the model, once you have trained the neural network, you use that neural network to play the game. You use the neural network to predict the value, that is a win percentage for any unseen state, and then choose the best move accordingly. For example, you have a decision to take, you have a decision to pick which move to make at a particular board position. You evaluate all the different moves and different board positions, and then take those different board positions and pass it to a neural network and get the value of get the win percentage for each of those positions, and then you choose the best move accordingly. This is it. Like you have at the end, like you have some training data, you have trained a neural network with the input as a state or the board position, and you get the output, like what is the value of it. You have the training data, you have the neural network which is trained by taking the inputs and the outputs, and you use that neural network to calculate the win percentage for any unseen states. And once we have the win percentage information, choose the best move, and you play the game using the neural networks, using the model based on neural networks. That's all. Neural network is all you need. Cool. So neural network, with the help of a neural network and with the help of trained model, you can play the game, and you can play a decent chess game. You can come up with an agent which can play a decent chess game. But the thing is, the game of chess is exponential in nature. The total number of moves, the total number of positions, board positions, total number of games, it's all exponential in nature. So we have to look at some efficient ways of training the neural network, collecting the training data and things like that. It's not like we randomly collect some training data of state and value pairs and we train the neural network. So let us look at some of the efficient ways and how to go about it. We start from the initial state. Take the chess example, and we start from the beginning. We start from the initial state and play one complete game. Let us say that complete game like takes this path in a tree of possible states and in a tree of possible games. Let us say it takes this one particular state, and and let us say we have played, that is one game, and let us say we have played another game which takes this particular path in the tree of all possible games. So now you have played two games and you have visited all these states, all these board positions by playing two games, and at each stage you keep track of total number of games played and total win percentages. For example, this particular state, let's say two games are played visiting this particular state, and out of two games, let's say you won one game and you lost another game. So you keep track of what are the number of games played for each visiting that particular state or that particular board position, and you keep track of how many wins it has resulted in, and you keep updating the win percentages accordingly. So once we have these win percentages, like we keep playing games from the beginning to the end, and you keep visiting the states. For each of the states you visited, keep updating the total number of games played and total wins, and parallelly keep training a neural network which will predict the win percentage for a given state. You keep playing the games, you keep visiting the states, you keep visiting the board positions, and at each state you keep updating the win percentages, and at each stage, like, you keep training the neural network, and that's all. Like, it is like one efficient way of like how you collect the training data and how you efficiently train a neural network. One caveat here is like so you don't play the games at random. Maybe initially you play the game at random, and at later stage you come up with more promising paths, and you exploit those paths as the game progresses, and like you play the games according to the certain policy distribution. So to give an example of chess, for example, in chess, the chess games which start with moving of the center pawns result in a better win percentages, rather than moving the edge pawns or the rook side pawns. So what you do is like you use that information. That information is obtained by playing some initial random games, and you use that information that moving center pawns will result in better win percentage, and as you progress you exploit those paths, you exploit more promising paths, and you play more games with that opening. So it is a kind of automated pruning of some less promising paths, and exploiting the more promising paths, and you make use of the policy distribution, updated policy distribution, and you keep playing the games, and you collect the training data for more promising paths, and parallelly you keep training the neural network, and like that is like one efficient way, and out of this, like you get a trained neural network model, like, which can play a decent chess game. So this is the textbook algorithm. We have a standard textbook for reinforcement learning, and this is the algorithm mentioned in the textbook. We initialize a policy phi, that is, policy is like which action to take, and the probabilities of those actions for a given state, and we initialize a approximator, that is a neural network, which takes states and weights, and it produces the value of that particular state. The weights of the neural network is here, and what you do is you loop, you play more number of games. You are in a particular state, take a particular action, and you get some reward. In this case, you can assume like there is zero immediate reward, and you keep playing, you generate one episode. That means like you keep playing game using certain policy, and 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 parallelly at each step you keep updating the neural network weights. You train the neural network model. You have the predicted value of the neural network. You have the approximate true value. The GT here is the expected return at that stage, that is approximate true value by using Monte Carlo methods. And you have the loss function, you have the total loss, and you have the gradients. You calculate the gradients and you update the weights. That's all. That's how you train a chess playing agent using neural networks and using reinforcement learning. All this looks not a very complicated stuff, right? It looks simple, but it's a very powerful concept. I'll explain about it in a minute. This is a generic concept. The concept of Monte Carlo approximation of value for a given state. This is a very generic stuff, and using a neural network to predict the value of a particular state, to predict the win percentage of a particular state. And this whole setup is a very generic stuff, and it can be applied not just to the game of chess. It can be applied to many different games. It can be applied to any of the video games or Go or any different games. And one thing to notice here is it finds the best move to win the game. It finds the global optimum, not the local optimum, given that like we played a good number of simulations. To stress this point, in the game of chess, for example, some of the local moves seems to be best. Like for example, capturing the opponent queen looks best at that stage, or like down two three steps. But after that, like you end up losing the game. You end up losing the game. But with this approach, you are not calculating the local optimal. You are calculating the global optimum. You are playing the games till the end, and you are trying to find the best move for the entire game, not just a best move couple of games and all. Most of the chess engines or humans can think like only beyond certain moves, like maybe probably 10 moves into future, not towards the end of the game. But like with this method, like you end up calculating the global optimum, not the local optimum. As I said, like it can be applied to many different games and many real world scenarios, and any improvement done, any betterment, any efficient ways of doing this whole process can be readily applied to other games. The same can be implemented for Go, the same can be implemented for video games, and etc. And it can be applied to many of the real world scenarios like robotics and all. And this method is like different from rule based engines like Deep Blue or Stockfish. The rule based engines, first of all, they take a lot of effort to program. You have to study the strategies, tactics of a particular chess game, and you have to put them into a computer program, and you have to design that computer program, carefully design it, and it takes a lot of effort. But even after putting a lot of effort, these custom rules are game specific. These strategies are game specific, and they cannot be easily applied to other games. So it's different from rule based engines, and it is much more efficient than the rule based engines. And the next thing is it gets better and better as we scale and with better hardware. As we get better hardware, we can perform more simulations and we get better gameplay intelligence. You can do more approximations. You can perform more simulations, and you can arrive at better approximations, and you can train a bigger neural network, and it scales really well. and that's all. Like we can get computers play many games at a superhuman level by using these very simple concepts. Cool. The thing is, Google DeepMind has already done it. It's not future. It's we are living in that times, like where we have a game playing agents which can play at a superhuman level for many different games. We are currently living in that times. With that, I end my presentation. Thank you all for watching the video.